All right, this is lesson IA-15. It's our final lesson on rational expressions. There are two objectives in this lesson, and I'm going to break this apart into two videos. The first lesson has to do with simplifying complex expressions, complex fractions. So there are many kinds of complex fractions. They are fractions that contain fractions within them. Problem number 1 shows a fraction within a bigger fraction, but there's a sum and difference going on. I call this type 2. Problem number 2 has a fraction on top and a fraction on bottom, but no sum or difference. Some are differences including the fractions, and I call this type 1. So depending on which type it is, I have certain method for doing it. Method 1 says to rewrite the complex fraction as a division problem and use your rules for division. Method 2 says to find the least common denominator for all the little fractions within the expression. Multiply every term in the numerator and every term in the denominator by it. Reduce the little products and simplify what is left. I'm going to go ahead and start with my problems. This first expression is what I call a type 2. So I'm going to use method number 2. So to simplify it, I have x over 11 minus a 1 over x minus 11. This method says if you've got sums and or differences involving any fractions, then you find the least common denominator of all the little denominators. Well, there's only one little denominator, and it is an 11. So I'm going to, using red ink, multiply the top by 11, but when I do, I'm going to distribute it so that this term also gets multiplied by 11. I'm going to multiply the bottom by 11, and I will distribute it so this gets multiplied by 11 also. It is the distributive property, but you can think of it as I multiply each term by the LCD. All right, for this first product, the 11s divide out, and I'm left with x. For the second, it's just 1 times 11 is 11. The denominator, I have 11 times 11 times x, which is 11x. Then I have a minus sign. 11 times 11 is 121. This is no longer a complex fraction, but it may be a fraction I can reduce. So I will ask, can I factor the numerator? The answer is no. Can I factor the denominator? The answer is yes. Factor out the 11. That gives you x minus 11. 11 was the GCF of these two terms. These divide out. When things divide out, although I don't always write them, it leaves behind little ones. And this gives me the expression 1 over 11. That's the expression simplified. But in this problem, and I think maybe this is our only problem, where we have to talk about the domain exclusions as well. So in this problem, when we talk about domain exclusions, I look at any little denominator to see if there is a value of the variable that could cause that denominator to become 0. This little denominator is a constant 11, and 11 is 11 and cannot become 0. The denominator of the big fraction, because remember I said any denominator, this can become 0. X minus 11 equals 0 means x is 11, and that is your domain exclusion. This complex fraction reduces to this provided x is not 11. And I really believe that may be the only question we have in simplifying complex fractions where it asks us to consider that. Let's look at number 2. This is what I would call type 1 because it is a single fraction over a single fraction. I rewrite that as a division problem. 10 over 8x divided by 5 over 8x. So I will keep 10 over 8x, change to multiplication, flip or invert the second fraction and see if I can reduce. Those divide out. 5 goes into itself once, 5 goes into 10 two times, and I am left with 2 over 1, which we would just write as 2. And so this problem is that simple. Problem number 3. Even though it looks more complicated than problem number 2, it is still a single fraction on top and a single fraction on bottom, and so I call it type 1, and I will write 7 over x minus 2 divided by x over x minus 2. I keep, I change, I flip. Common factor of x minus 2 divides out, and I am left with 7 over x. Type 1 typically is the easier kind to write down. Let's look at number 4 here and see. I have a single fraction on top, but on the bottom I have two fractions, finding a difference, so this is type 2. So I'm going to write this expression down, 5x squared minus y squared over xy all over 5 over y minus 1 over x. Look at the denominators. xy, just y, just x. The LCD is xy, because remember you need one of every different kind of factor to get the least common denominator. So I'm going to multiply xy times the numerator, xy times this term of the denominator, and xy times this term of the denominator. For the numerator, the xy's divide out, and I'm left with 25x squared minus y squared over this part of the denominator, the y's divide out, and I'm left with 5x. This part of the denominator, the x's divide out, and I'm left with minus y. It may be finished, but look at that numerator. Is that factorable? And the answer is yes. That is the difference of squares. So I'll put 1 plus, 1 minus. So I have 5x, for some reason things are disappearing, 5x plus y and 5x minus y all over 5x minus y. And I have no idea why things are disappearing, but they are. I have a common factor. I better do this before the whole thing erases. The 5x minus y's are common factors, and that leaves us with the simplified expression of 5x plus y. And I hope whatever that problem is goes away. Remember, I said that we're not going to ask about domain exclusions in the rest of these problems. Problem number 5, single fraction over single fraction. It is a complex fraction, but it is what I would call type 1. And when they're type 1 with single over single, I write it as a division problem. X plus 7 over 4 divided by 4x minus 1 over 12. Keep x plus 7 over 4. Change to multiplication, 12 over 4x minus 1. This numerator cannot be factored. This denominator cannot be factored. Are there any common factors anywhere? Well, 4 goes into 4 once. 4 goes into 12 3 times. That means I have 3 times x plus 7 over 4x minus 1. If you wanted to leave the 4x minus 1 in parentheses, you could, or you can write it like that. Nothing can be reduced. Let's look at number 6. This also is a complex fraction, but I have 1, 2, 3, 4. I have more than just a fraction over a fraction. So I will call this type 2, and I will look for the LCD of the little denominators. I have an x squared, an x squared, and an x. So I need the higher power, which is x squared. So I'm going to write this down. 3 over x plus 1 over x squared over 9 over x squared minus 1 over x. Common denominator is x squared. I multiply it here, but it's as if I distribute it. So I'll multiply it here and here and here. And when I multiply the top and the bottom by the same quantity, that's really 1. So I've just multiplied by the identity. That I'm just trying to justify why it was okay for me to do that. All right. If I simplify this, x goes into x squared with 1x left over, meaning that I have x times 3, or 3x. In this part, I have my plus sign. The x squareds divide out, and I'm left with 1. The bottom, the x squareds divide out, and I'm left with 9. I have a minus sign. This x divides out one of those x's, and I have a single x left over. I cannot factor the numerator. I cannot factor the denominator. I'm done. So, number 6 was pretty short, even though it was type 2. Let's look at number 7. I have a number minus a fraction, and then a fraction minus a number. Oh, this is definitely type 2. So, little denominator of y, little denominator of y squared. The LCD is y squared. So I have 2 minus x over y over x squared over y squared minus 4, and I'm going to multiply by the LCD, which is y squared times this, y squared times this, y squared times this, y squared times this. Okay, got a little problem. Let me resolve it. Problem resolved. I have this product, which is 2y squared. Nothing divides out. But in this product, this y divides out with one of those y's, leaving me with an xy term over here. The y squareds divide out, and I have x squared minus, I can just multiply for y squared because there was nothing to divide out. Looking at this, I think there's some factoring I can do. The numerator, the GCF, is y, and that will leave me with 2y and minus an x. The denominator is the difference of squares, so it's going to be x plus 2y times x minus 2y. Now these two terms are not equal because there is no commutative property of subtraction. These terms are actually opposites. You can divide out opposites, but you leave a negative 1 behind, usually just written as a negative sign. But there is a negative left behind if you divide out opposites. Now, if you had, just as an aside, if you had x plus y and y plus x, those are not opposites. Those are equal. Those have the same value. But if you have x minus y and y minus x, those are opposites. So you can divide out opposites if you leave a -1. That means that you have negative y over x plus 2y. All right, and that the negative sign can be there. You could have written it as negative the fraction y over x plus 2y. Either way, remember, these y's are not factors to be divided out because y is not a factor of the entire denominator. So if you're worried about that, put it in parentheses and know that you can never divide out part of what's in parentheses. All right, that's complex fractions. I'm going to stop the video and pick back up with the second part.